Hi, our third lesson in Chapter 1 is a little bit more on functions and graphs of functions. So we're going to be looking at several different topics today. The first of which is areas or ranges where the function is increasing or decreasing. And first off, we're going to ask you to look at the function that's shown, and it is a function, folks, since no vertical line can hit it in more than one spot. For what values is it increasing? Well, as you just inspect this graph, you can see that as x goes from a to b, that function is increasing. So a way to write that in interval notation is this. It goes from x equals a to x equals b. You could also write it this way: a is less than x is less than b. Those all talk about the x area in which this thing is making an increasing turn. There is another though, and that the second area of increase is when x is c or larger, because you can see that the function itself is increasing as c gets bigger. We'll write that as c toward infinity. And I wanted to talk a little bit about the parenthesis notation here. Parentheses mean that that value c is not actually part of the range that you're interested in, because at point c this function is not increasing, but after it is. We could also write this in the extended inequality by writing c is less than x is less than infinity. Our textbook goes with this interval notation. So take a look again, and let's see if we can have you list which values of x this function is decreasing under. And I think that you should be able to see two areas of decrease. Why don't you pause the tape and see if you could write those down for a moment. The first would be from negative infinity through a. As x moves from negative infinity to a, this function itself is dropping down. So negative infinity to a is one area of decrease. The second is between the two x values b and c. As x moves from b towards c, the function is decreasing. If the end of an interval is included, you should use the square brackets. You'll notice we did not use them anywhere here because our interval ends are not included in our ranges. Actually, you can't really have an end to infinity. Otherwise, you do what we did, which is use parentheses. Points E and D. As you look at those 2 points in the graph, E here, D here, both of them are at the bottom of a trough in this function. They are minimums. That is, they are low spots in this graph. I want to put a little proviso on there. Point E is a relative minimum. And we say relative because it's not the very lowest point in this function. Just in the area in which it lies, it's the lowest point there. We would call D an absolute maximum, since there is no point in this function that will ever go lower than D. So D is an absolute minimum. Good. All right, the point F, as you can well imagine, is a maximum. Particularly, it's a relative maximum. Why relative, you might ask? Well, there are many other points in this function that actually have higher y values than point F does. Just in the area in the graph where point F appears, it's the highest, so a relative maximum. Your calculator's second trace menu includes a way to find those. The keystrokes that you would use on the TI-84 are second, trace, and then pick max or min. You have to go through a procedure of setting a left and right boundary around the, say if we were going for this one, you'd move your cursor here left of the minimum and press enter, move right of the minimum and press enter, and then on the TI-83 and 4 you have to press enter one more time. So it's second trace, min, set the boundary, and then enter one more time, and it'll give you the x value at which that minimum occurs. Actually gives you the y value as well. So it shows you the x where it happens, and it tells you how high y is there. All right, I'm going to move on. And we want to talk just a little bit, as we said, there's quite a few different notions about functions in this lesson, even in odd functions, and you can see I have a definition prepared for you. Even functions, and this one is an even function, have this criteria. They have reflection symmetry over the y-axis. That is, you can consider the y-axis to be a fold line in this function. This half would lie directly on top of this half. Even functions have reflection symmetry over the y-axis. Later in this class, but why not today, since it will help us today, we're going to learn that their equations, if a function is even, all of the exponents in that function will be even. Which sort of kind of makes sense. Odd functions, on the other hand, and here's an odd function. Odd functions don't have reflection symmetry. Instead, they have 180-degree rotational symmetry about the origin. That is, you can imagine pulling that handle 180 degrees down here, and you have this thing rotating right back into the same position that it's in now. 180-degree rotational symmetry. Their equations, odd functions that is, have only odd exponents. They cannot have a constant term. And if you think about that for a minute, you'll see right away why that has to be. They have to pass through the origin in order to have that rotational symmetry. So if we had a constant, something that lifted the curve up this high perhaps, then it wouldn't rotate about the origin anymore. So even functions have all even exponents in their equations. Odd functions have all odd exponents with no constant. It's okay for the even function to have a constant, and with that said, we can use our calculator to look at these functions to decide whether they are even, odd, or neither, or we can use the rules. And I'm looking at this one and thinking, here's an exponent of 4, an exponent of 2, and a constant. Now, we've said before that you could imagine this as being multiplied by x to the 0th power, which is a value of 1. And I'll tell you, those are all even exponents. This is an even function, and if we do graph it on our calculator, 2x to the 4th plus x squared minus 5, we would see that it has some sort of parabolic shape. I'm going to grab my calculator, 2x to the 4th plus x squared minus 5. And I'm going to go ahead and graph that. So I need to add a page that's got a graph. Okay, so we are 2x raised to the 4th power plus x squared minus 5. Good. We hit enter, and here's our function, and sure enough you can see that even function symmetric about the y-axis. Alright, the next one on our list, I'll bet you that we can figure out without looking. However, you take a second. We have an exponent that's a 5 and an exponent that's a 2. What do you think? Even, odd? Yeah, you guessed it. This is neither. Okay, if it has a mix of even and odd exponents, it's not either even or odd. That doesn't make it bad in any way. It just means it doesn't fit either of these two descriptions. And then the final one, the equation is y equals, or h of x equals negative 2 times x. Take just a second and get a picture of this in your mind's eye. Negative 2x. That's like a line, folks. It's a line that does sloping downward through the origin. And I would ask you, what do you think? Even or odd? Is this a reflection across the y-axis? Does this have rotational symmetry about the origin, or neither? And I hope that you're thinking right now, this is an odd function. It does have the rotational symmetry. It also has an exponent of 1, which is an odd number. So even functions reflect across the y-axis and have all even exponents. So they're always going to have end behavior that is this parabolic kind of behavior. They may have some interesting stuff in the middle, but at the edges, they're going to have to be parabolas. Odd functions have to go through the origin. They have to have rotational symmetry. Their equations will only ever have odd exponents with no constant. Let's go on. The next type of function we're going to look at today is a piecewise function, and if you remember this from your algebra class, you may be cringing right now. They were never our favorite things. This is the cell phone plan that we're going to be looking at, and I'm going to try and read while I'm writing here. $20 per month will buy you 60 minutes of airtime. Additional time is 40 cents per minute. I'm not sure that's the plan I want, but that's the one we have here. And we are supposed to graph that. So for the first 60 minutes, so I guess we should put labels on our graph. Minutes, and this is cost, or dollars. Up through 60 minutes, it looks like the scale is 20 on here. So 20, 40, 60. Here's the 60-minute mark. It's going to cost us $20 up to and including right there. Okay. Once we get past that 20, then we have to spend 40 cents more per minute. And to help me decide how much my plan is going to cost, I'm going to just put some values for minutes here that I'm interested in. 80 minutes, 100 minutes, just enough so that we can get some idea of what the rest of this graph is going to look like. So if I use 80 minutes, I'm paying $20 for sure because that's the base price. And then it is 40 cents for every minute above 60. Well, I'm 20 minutes above 60, so I have to have 40 cents for 20 more minutes. And as you look at that little multiplication, that's going to be 0.4 times 20. That's $8. So $28 is this guy. And that was at 80 minutes. 28, oh, it's up in there somewhere, almost to the 30 mark, but not quite. At 100 minutes, we're paying the base 20, and we are 40 minutes above the minimum, so 0.4 times 40. Well, that's going to be $16. 20 and 16 is 36. 36, oh, maybe in there somewhere. And at 120, we pay the base 20. We have to pay 40 cents for 60 minutes. And that's going to be $24. So we're going to 44 right in here. Now, our graph is flat, even though mine looks a little scribbly. But as soon as we get past the 60-minute mark, that price starts climbing, and it climbs at the same rate from there on out. A piecewise function, you can see this is broken up into two pieces. The first piece is through those 60 minutes, and then the second piece, any minutes beyond 60. If we were going to write this in function notation, we'd write perhaps c of x, cost function, is equal to, and we kind of have to write this rule in pieces because this function comes in pieces. C of x is equal to $20 when x is less than or equal to 60 minutes. After that, we pay $20 plus 40 cents for each minute, and our minutes will be x minus 60. Okay, that's what we did every time. We subtracted 60 from this number, we multiplied by 40 cents and added it to the 20 that we had. This part of the function is good for x's that are greater than 60. So our piecewise function is broken up into two parts, and we write separate rules for each part. You might consider this part to be part 1, right here, and this rule, part 2. All in here. Whoops, all in there. Good, piecewise functions, and I'm thinking that you probably remember that from your Algebra 2 class. I'm sure that you at least graphed or looked at a couple of piecewise functions. let's take a look at the next one here. We are supposed to graph this piecewise function. No story problem anymore, just a graph of it. It says that when, oh, by the way, 3 pieces. So there's piece 1, the middle one, piece 2, third one, piece 3. Piece 1 happens when x is less than or equal to -5. And folks, that's anything that's to the left of that x equals -5 line. So this is going to be my first piece. The second piece goes from -5 to x of 4. So x of -5 to x of 4. Here's that second piece. And then the third piece is anything beyond 4 or x above 4. All right, let's see if we can't graph this. When x is -5 or less, the value of the function is just plain old 2. No matter what x you have, the value of the function, the y, is 2. And folks, that's anywhere right along that line. Our rule said less than or equal to, so I'm going to just remind you, a closed dot goes there. When x is -5, this function has a value of 2. If we get into the next part of this, though, when x is between -5 and 4, then our value, our function value, will be the x that we're at plus 4. Now, I said that -5 was contained in the first part of this function, and it is. But if we want to graph this correctly, we have to think, okay, this function doesn't, this part doesn't have a value at -5, but I need to know where it would be if it were going to, because that's where things start here. So I'm going to put -5 into my function rule. -5 plus 4 is -1. So right here on the line, when x is -5, this function should have had a value of -1. Open circle. This is how it's defined in part 1. In part 2, it's not defined, but this is where we would start. A good way to graph this thing is to look at the other boundary. At the other end, x of 4. So now we're going to talk about where this second part hits out here. If x is 4, then we would get 4 plus 4, 8. And we would want ourselves a little open or closed? Closed dot right there. The second part of this function goes, whoops, I didn't draw a very good line. X is less than -5 here. -5 to x to 4, right? That's that part. And all that's left is now this. When x gets bigger than 4, we want to graph, or the y of it will be half of that. So again, I'm going to look at what happens at the boundary when x is 4. According to this, half of 4 is 2. So we should have an open circle here. That point is not really part of this. However, it gives us a place to start this third section. We need to pick another point out there, another x. So maybe x of 10. If we had x of 10, then y would be half of 10, which is 5. And that would put us there. I do this because we need to have a way to see where this function is headed. So we've graphed our piecewise function, and in this part of it, x was greater than 4. 3-piece function, and each of them had a slightly different definition. Piecewise, kind of strange. The last thing that we're going to talk about today is another piecewise function. You can see that this function I've graphed is all split up in 2 pieces, many pieces. In fact, this is a member of the step function family, it's called, because it looks like a set of staircase steps. This is actually called the greatest integer function. Greatest integer. And it's represented in symbols this way. F of x equals, and it's 2 brackets, x in the middle. Greatest integer. In words, what this function does is f of x will be, or is, the greatest integer. That means the largest. The greatest integer less than or equal to x. the greatest integer less than or equal to x. So as you think about that, that's kind of an odd definition. My table, instead of just showing single x values here, it shows ranges of values, because that's how this thing works. As long as x is between -3 and -2, and if you think about that, that's right in here. There's -3, there's -2. As long as x is between -3 and -2, this function has the value -3. It's the greatest integer that's less than or equal to this range of values. So if we are at 2.5, the biggest integer that's less than that is still -3. F of x is -3 here. As you look at this, you can see pretty quickly what's going to happen when x goes between -2 and -1. Anywhere through that, the y value will be -2, because that's the next greatest integer less than or equal to anything in this range. And you can see it does go up in stair step and on down. Between 0 and 1, the next greatest integer would be 0, then 1, 2, and 3, etc. The greatest integer function is similar to many problems where you paid different amounts of money for different time allocations. I guess that's like if you think about parking lot problems. I had to take my mom to the airport the other day. So parking was $2 for the first half hour, and then $1 for every hour after that. That's going to rise just like one of these step functions. It's going to start out at $2 for the first half hour, and then it's going to jump $1 every hour after that. So the domain in a function like this is all real numbers. Any x can be input, but the range on this is only the integer values. You only ever pay a round amount. Sometimes I think integers. Sometimes I wish they did that with like prices of hamburgers, because I'd much rather pay $1 than I would pay 99 cents, or I'd rather pay $2 than $2.09, right? The greatest integer would be nice in hamburger land, but I guess they don't do that. Okay, we're at the end of our lesson. We'll ask you to look at the U-Try for this lesson and submit as soon as you can. Tomorrow in class we will be working with functions and graphing them. So have a great night.